Last week we have studied monolithic versus distributed architecture styles. In monolithic, I have introduced the layer, pipe and filter, as well as microkernel architecture styles. This week, we will continue to discover some distributed architecture styles, such as service-based and microservice architecture styles. At first, we will take a look at service-based architecture style. Service-based architecture is considered as one of the most practical architecture styles, mostly due to its architectural flexibility. Although service-based architecture is a distributed architecture, it doesn't have the same level of complexity and cost as other distributed architectures, such as microservices or event-driven architecture, making it a very popular choice for many business-related applications. Services within this architecture style are typically coarse-grained portions of an application, usually called domain services, that are independent and separately deployed. Services are typically deployed in the same manner as any monolithic application would be, such as an ER file, WAR file, or assembly, and as such do not require containerization, although you could deploy a domain service in a container such as Docker. Because the services typically share a single monolithic database, the number of services within an application context generally range between 4 and 12 services, with the average being about 7 services. The basic topology of service-based architecture follows a distributed macro-layered structure consisting of a separately deployed user interface, separately deployed remote coarse-grained services, and a monolithic database. In most cases, there is only a single instance of each domain service within a service-based architecture. However, based on scalability, fault tolerance, and throughput needs, multiple instances of a domain service can certainly exist. Multiple instances of a service usually require some sort of load balancing capability between the user interface and the domain service. Services are accessed remotely from a user interface using a remote access protocol. While REST is typically used to access services from the user interface, messaging, remote procedure call, or even SOAP could be used as well. While an API layer consisting of a proxy or gateway can be used to access services from the UI or other external requests, in most cases the user interface accesses the services directly using a service locator pattern embedded within the UI, API gateway, or proxy. This allows services to leverage SQL queries and joins in the same way a traditional monolithic layered architecture would. Because of the small number of services, 4 to 12, database connections are not usually an issue in service-based architecture. Database changes, however, can be an issue. The section database partitioning describes techniques for addressing and managing database change within a service-based architecture. Many topology variants exist within the service-based architecture style, making this perhaps one of the most flexible architecture styles. For example, the single monolithic user interface, as illustrated in the first part of the diagram, can be broken apart into user interface domains, even to a level matching each domain service. These user interface variants are illustrated in this figure. Similarly, opportunities may exist to break apart a single monolithic database into separate databases, even going as far as domain-scoped databases matching each domain service. In these cases, it is important to make sure the data in each separate database is not needed by another domain service. This avoids inter-service communication between domain services, something to definitely avoid with service-based architecture, and also the duplication of data between databases. Finally, it is also possible to add an API layer consisting of a reverse proxy or gateway between the user interface and services, as shown in this figure. This is a good practice when exposing domain service functionality to external systems or when consolidating shared cross-cutting concerns and moving them outside of the user interface, such as metrics, security, auditing requirements, and service discovery. Because domain services in a service-based architecture are generally coarse-grained, each domain service is typically designed using a layered architecture style consisting of an API facade layer, a business layer, and a persistence layer. Another popular design approach is to domain partition each domain service using subdomains similar to the modular monolith architecture style. Regardless of the service design, a domain service must contain some sort of API access facade that the user interface interacts with to execute some sort of business functionality. The API access facade typically takes on the responsibility of orchestrating the business request from the user interface. For example, consider a business request from the user interface to place an order, also known as catalog checkout. This single request, received by the API access facade within the order service domain service, internally orchestrates the single business request, place the order, generate an order ID, apply the payment, and update the product inventory for each product ordered. In the microservices architecture style, this would likely involve the orchestration of many separately deployed remote single-purpose services to complete the request. This difference between internal class-level orchestration and external service orchestration points to one of the many significant differences between service-based architecture and microservices in terms of granularity. Domain services are coarse-grained, using regular ACID, atomicity, consistency, isolation, durability, database transactions involving database commits and rollbacks to ensure database integrity within a single domain service. Highly distributed architectures like microservices usually have fine-grained services and use a distributed transaction technique known as base transactions, basic availability, soft state, eventual consistency, that rely on eventual consistency and hence do not support the same level of database integrity as ACID transactions in a service-based architecture. Although not required, services within a service-based architecture usually share a single, monolithic database due to the small number of services, 4 to 12. This database coupling can present an issue with respect to database table schema changes. If not done properly, a table schema change can potentially impact every service, making database changes a very costly task in terms of effort and coordination. Within a service-based architecture, the shared class files representing the database table schemas, usually referred to as entity objects, reside in a custom shared library used by all the domain services, such as a JR file or DLL. Shared libraries might also contain SQL code. The practice of creating a single shared library of entity objects is the least effective way of implementing service-based architecture. Any change to database table structures would also require a change to the single shared library containing all of the corresponding entity objects, thus requiring a change and redeployment to every service, regardless of whether or not the services actually access the changed table. Shared library versioning can help address this issue, but nevertheless, with a single shared library it is difficult to know which services are actually impacted by the table change without manual, detailed analysis. One way to mitigate the impact and risk of database changes is to logically partition the database and manifest the logical partitioning through federated shared libraries. Notice in this figure that the database is logically partitioned into 5 separate domains: common, customer, invoicing, order, and tracking. Also notice that there are 5 corresponding shared libraries used by the domain services matching the logical partitions in the database. Using this technique, changes to a table within a particular logical domain, in this case, invoicing, match the corresponding shared library containing the entity objects, and possibly SQL as well, impacting only those services using that shared library, which in this case is the invoicing service. No other services are impacted by this change. The use of the common domain and the corresponding common_entities_lib shared library used by all services. This is a relatively common occurrence. These tables are common to all services, and as such, changes to these tables require coordination of all services accessing the shared database. One way to mitigate changes to these tables and corresponding entity objects is to lock the common entity objects in the version control system and restrict change access to only the database team. This helps control change and emphasizes the significance of changes to the common tables used by all services. Tip: make the logical partitioning in the database as fine-grained as possible while still maintaining well-defined data domains to better control database changes within a service-based architecture. To illustrate the flexibility and power of the service-based architecture style, consider the real-world example of an electronic recycling system used to recycle old electronic devices, such as an iPhone or Galaxy cell phone. The processing flow of recycling old electronic devices works as follows. First, the customer asks the company, via a website or kiosk, how much money they can get for the old electronic device, called quoting. If satisfied, the customer will send the electronic device to the recycling company, which in turn will receive the physical device, called receiving. Once received, the recycling company will then assess the device to determine if the device is in good working condition or not, called assessment. If the device is in good working condition, the company will send the customer the money promised for the device, called accounting. Through this process, the customer can go to the website at any time to check on the status of the item, called item status. Based on the assessment, the device is then recycled by either safely destroying it or reselling it, called recycling. Finally, the company periodically runs ad hoc and scheduled financial and operational reports based on recycling activity, called reporting. This figure illustrates this system using a service-based architecture. Notice how each domain area, identified in the prior description, is implemented as a separately deployed independent domain service. Scalability can be achieved by only scaling those services needing higher throughput, in this case, the customer-facing quoting service and item status service. The other services do not need to scale, and as such only require a single service instance. Also notice in how the user interface applications are federated into their respective domains: customer-facing, receiving, and recycling and accounting. This federation allows for fault tolerance of the user interface, scalability, and security. External customers have no network path to internal functionality. Finally, notice in this example that there are two separate physical databases, one for external customer-facing operations and one for internal operations. This allows the internal data and operations to reside in a separate network zone from the external operations, denoted by the vertical line, providing much better security access restrictions and data protection. One-way access through the firewall allows internal services to access and update the customer-facing information, but not vice versa. Alternatively, depending on the database being used, internal table mirroring and table synchronization could also be used. Service-based architecture is a domain-partitioned architecture, meaning that the structure is driven by the domain rather than a technical consideration. Being a distributed architecture, the number of quanta can be greater than or equal to 1. Although service-based architecture doesn't contain any 5-star ratings, it nevertheless rates high for stars in many important and vital areas. Breaking apart an application into separately deployed domain services using this architecture style allows for faster change, agility, better test coverage due to the limited scope of the domain, testability, and the ability for more frequent deployments, carrying less risk than a large monolith deployability. These three characteristics lead to better time to market, allowing an organization to deliver new features and bug fixes at a relatively high rate. Fault tolerance and overall application availability also rate high for service-based architecture. Scalability only rates 3 stars due to the coarse-grained nature of the services, and, correspondingly, elasticity only 2 stars. Simplicity and overall cost are 2 other drivers that differentiate this architecture style from other, more expensive and complex distributed architectures, such as microservices, event-driven architecture, or even space-based architecture. This makes service-based one of the easiest and cost-effective distributed architectures to implement. While this is an attractive proposition, there is a trade-off to this cost savings and simplicity in all of the characteristics containing 4-star ratings. The higher the cost and complexity, the better these ratings become. Service-based architectures tend to be more reliable than other distributed architectures due to the coarse-grained nature of the domain services. The flexibility of this architecture style combined with the number of 3-star and 4-star architecture characteristics ratings makes service-based architecture one of the most pragmatic architecture styles available. While there are certainly other distributed architecture styles that are much more powerful, some companies find that power comes at too steep of a price, while others find that they quite simply don't need that much power. Service-based architecture is also a natural fit when doing domain-driven design. Maintaining and coordinating database transactions is always an issue with distributed architectures. However, service-based architecture preserves ACID transactions better than any other distributed architecture due to the coarse-grained nature of the domain services. There are cases where the user interface or API gateway might orchestrate two or more domain services. And in these cases, the transaction would need to rely on sagas and base transactions. However, in most cases, the transaction is scoped to a particular domain service, allowing for the traditional commit and rollback transaction functionality found in most monolithic applications. Lastly, service-based architecture is a good choice for achieving a good level of architectural modularity without having to get tangled up in the complexities and pitfalls of granularity. As services become more fine-grained, issues surrounding orchestration and choreography start to appear. Both orchestration and choreography are required when multiple services must be coordinated to complete a certain business transaction. However, because services within a service-based architecture tend to be more coarse-grained, they don't require coordination nearly as much as other distributed architectures.